Hi, my name is Samantha Nelson, and today we're going to be going over all the different reactions that we've learned in organic chemistry during week 1. So here are a list of the different reactions that we looked at during week 1. You can see it's halide reactions, whether that's aryl or vanillic halides, NAS, which is nucleophilic aromatic substitution. That includes elimination, addition reaction, and addition elimination reaction. We have coupling reactions, which is the Suzuki reaction, Nagashi reaction, the Still reaction, and the Sonogi-Shira reaction. Lastly, there's some fundamental reactions, which includes ligand reactions, ligand dissociation, association, ligand substitution, ligand insertion, as well as oxidative addition, reduction elimination, and beta elimination. So all these different reactions have different applications. In aryl halides, they're actually the chloro-aryl compounds are used as insecticides, herbicides, fungicides, bactericides. Vanillic halides are frequently used to form Grignard reagents, which actually are really important in pharmaceutical production, and it was largely discussed last quarter in Ochem 2. Next, the nucleophilic aromatic substitution is used to synthesize intermediates, and those intermediates are used as precursor compounds for pharmaceutical and industrial products. Coupling reactions, these are all pretty used frequently for cost-effective pharmaceutical synthesis of drugs. Nagashi reaction is used pretty commonly in the synthesis of drugs to treat asthma. And the Still and Sonogi-Shira reaction is used of the synthesis of natural products. For the fundamental reactions, it was hard to find industrial applications. However, a bunch of the ligand reactions were used in biomedical for pharmaceutical drugs. Oxidative addition was used in catalyst reactions. Ligand substitution was actually found for the synthesis of nanoparticles. And beta elimination helps with the formation of polymers. So now that we've covered the basic applications of all these different reactions, I'm going to quickly go over the reaction, its concept, and the mechanism that we've learned. So in this halide reaction, first, both of them follow E2 reactions, and they do not follow SN1, SN2, or E1 reactions due to the formation of carbocation and stability issues. So for the aryl halides, they form a benzene ring, which is actually a benzene ring, except it has a triple bond formation. So you can see that in this mechanism, we have an NH2 is going to grab that proton, and there's going to be a shift in the electron movement, which is going to form this negative charge because of the electrons leaving from the hydrogen bond. And due to those, the rearrangement of electrons for stability purposes, it's actually going to kick out this halogen or halide, and it's going to form this benzene ring, which is, you can see here by that triple bond. This group is known as the loss of a leaving group. For vanillic, you can see that it's going to be characterized by the addition elimination of bromine twice. So first, they're adding bromine and a Markovnikov to the most substituted. Next, you're going to add the second Markovnikov to the other side of that double bond, and by doing so, you're going to make this single bond. So you're essentially breaking those bonds using two equivalent NaH to either take out one hydrogen and then in a second round take out the other hydrogen. You're able to form this triple bond that you see here. So in that way, both of them are elimination, considering they're getting rid of the halide, and then they're forming some type of triple bond instead. Next, we're going to be looking at nucleophilic aromatic substitution, and this includes elimination addition and addition elimination. The concept is pretty straightforward. In elimination addition, you're first eliminating and then you're adding. So you can see here is that you're going to be eliminating the bromine from the aromatic and then adding on the compound that you would like. So again, you're going to be using NH2 to remove a proton and shift electrons on the aromatic ring. Due to rearrangement, you're going to form that you're going to form that benzene ring as well, and then you can add on your amine group. What's interesting about this elimination addition reaction is that it actually can happen in two different areas. You can add the second NH2 from one side, or you can add it from the other side. In this place, I chose to add it from position 1. However, position 2 would look like this, and it does have a 50-50% chance of forming in this way or forming in this way. You can see that this is only 1 carbon away, but this is 2 carbons away. So we would say that this is 1,4 and this is 1,3 addition. Next, we're going to be looking at addition-elimination reaction. So an addition-elimination reaction, it's pretty straightforward. Again, you're going to be adding on that compound. You can see here that the addition of the OCH3 group caused a rearrangement of electrons, making this aromatic negative due to the valence electrons pairs. And then what we're going to do is we're going to go through rearrangement. So by moving the electrons, we're able to get it so these electrons are right next to that addition. And by doing this last rearrangement of bonds, we're going to be able to cause this fluorine to move because of loss of a leaving group, creating this compound right here, which technically just substitutes the fluorine with the compound that you wanted. Next, we're going to be taking a look at coupling reactions. For the Suzuki reactions, it's going to be characterized by an aryl or vanillic boronic acid with an aryl vanillic iodine or bromide. So you can see here that we're going with bromine, and we're going to try and be coupling these two compounds. As you can see, I've circled the carbons on which they couple. So you can see that this bromine dissociates from the compound, and so does this molecule right here. And due to coupling on these specific places, you're going to end up with this compound right here. An interesting note is that all of these different coupling actually uses palladium as a catalyst, which is really important in recognizing these coupling reactions from the rest that we've learned. Next is Nagashi reaction. It's actually transmetallation reaction. So you can see here that you're going to be using zinc bromide during the coupling, and these are the two carbons that are going to be connected. Obviously the chlorine and zinc bromide are going to be leaving this compound right here. You can see that this is where the chlorine was and this is where the zinc bromide was. Next is the still reaction. What's nice about still is that there is no rearrangement. So you can see that from this compound we have made from this compound it was produced by using these two right here. This carbon coupled with this carbon, causing this compound and bromine to leave, again catalyzed by palladium, which is a common theme here. You can see that this is actually a diene if you look here, and so that can be used to synthesize a diene and therefore use a dienophile to create a compound. Lastly is Sonogashira reaction. It's an organocuprate reaction, so it's the only one that uses the cuprate, copper, and iodine as a catalyst in the reaction. Again, as long as with the other ones, you can see that the iodine and this carbon will couple, the carbon on the iodine and the carbon alkyne will couple with the help of the palladium catalyst and form this compound right here. Again, you can see this is where they coupled. So that's it for the coupling reactions. Lastly, it's fundamental reactions. So ligand dissociation association. The electron count on the metal changes. You can see right here is what we're looking at. So this is the oxidation state. You can see that the oxidation state on palladium is 0. It will continue to be 0. However, the electrons change. So palladium is 10. The ppH3 is going to be 2. So that's 4 times ppH3. So we have total electrons as 18. However, if we remove a ppH3, it becomes 16 in here and 2 here. So we can see that the number of electrons in that compound will change with the removal of ppH3, which was a ligand. Next is oxidative addition. So you can see that during oxidation, you're going to be gaining electrons. You can see oxidation state here on palladium is 0. And then as we move to the addition of this compound, it becomes +2. You can see that the electrons in this compound are 14. But as you are adding a halide group and adding an aromatic group, it becomes 16. So to compensate, palladium needs to get a +2 charge. Next is ligand substitution. And this is can either be 1,1 or 1,2. Oh, sorry. It's a transmetallation reaction. So here we can see that there is going to be no change in electrons. You're essentially just you're swapping the groups. So this ligand is substituted for the CH3. Ligand insertion could be either 1,1 or 1,2 insertion, depending on the bonding. So you're going to have a metal is going to bond to a compound, R group, and it can either be bonded in spot 1 or bonded in spot 2, depending on where you do it. There's going to be reductive elimination, and this is where the electron count on the metal changes. So you can see here that palladium has a +2 charge, but as soon as it's removed from this compound, it's going to have a 0. It's going to have no charge or no oxidative state. And then in beta elimination, it's syn elimination. So you're going to take away this proton. Again, you're going to have the proton transfer and electron shift to create that double bond that we see. So those are all the reactions that we did during week 1. Thank you for listening, and goodbye.